Every year, dozens of nuclear submarines get retired around the world. Steel giants weighing over 10,000 tons. Inside each one sits a reactor pumping out hundreds of megawatts. But what happens when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that lasts for months? Temperatures here hit 14,000 degrees Fahrenheit. A mistake isn't measured in seconds, it's measured in centuries. In this video, you'll see the decommissioning process from the first cut to the last ton of melted metal, and find out what becomes of a submarine giant's armor. The process begins with the most dangerous stage, removing the spent nuclear fuel. The submarine is moved into a special enclosed dock. Around it, a real scientific laboratory unfolds. This is a battle against invisible radiation. It doesn't last days, it lasts months. Inside the reactor core are fuel assemblies. They've kept this monster alive for decades. Each assembly is a bundle of thin zirconium tubes, about half an inch in diameter. Inside, uranium dioxide pellets. One assembly is 13 feet long. Weight, 660 pounds. The reactor holds 100 to 120 of them. They're removed using remote manipulators. Each assembly emits a lethal dose of radiation, 500 roentgens per hour at 3 feet. That'll kill a person in an hour. The assembly is lifted by a crane rated for 20 tons and lowered into a lead container. Container wall thickness, 10 inches of pure lead. Container weight, 17,000 pounds. Only lead stops gamma radiation. The containers are loaded into special rail cars with water cooling and shipped to temporary storage. This stage takes 3 to 4 months of continuous work. If you're interested in seeing how things built for war get taken apart, subscribe to the channel. Here we show you production processes hidden from view. Once the fuel's extracted, it's time for the reactor compartment. This is a massive section of the sub. Weight, 1,500 tons. Length, 33 feet. Diameter, 30 feet. Engineers don't dismantle the reactor piece by piece. Too dangerous. The metal itself is radioactive. Neutron flux from the operating reactor bombarded the steel for years. Iron atoms transformed into radioactive isotopes, so they cut out the entire compartment whole. They use oxyacetylene torches. Flame temperature, 5,800 degrees Fahrenheit. Mix of acetylene and oxygen. Feed pressure, 217 pounds per square inch. The torch burns through 3-inch thick steel in 10 minutes. They cut in a ring around the compartment. 2 cuts, forward and aft. You get a cylinder. All technological openings are welded shut with half-inch steel plates. Welding, electric arc, 1/4-inch diameter electrodes. Current, 350 amps. You get a sealed capsule. It's lifted by a 200-ton crane and loaded onto a barge. The barge is towed to a burial site. In Russia, that's Novaya Zemlya. In the US, Hanford site. There, the capsules are placed in concrete trenches 65 feet deep, covered with earth on top. They'll sit there 300 years until radiation levels drop to background. Decontamination is the longest phase. The reactor compartment's cut out and shipped off, but the work's just beginning. Decades of coolant circulation left their mark. Thousands of feet of primary loop piping, pumps, heat exchangers, steam generators, all of it contaminated. Radioactive isotopes soaked into the metal. That's induced radiation. Teams in protective suits scan every foot, hunting for hotspots, areas with elevated readings. They use DP5B dosimeters. Sensitivity, 0.01 milliroentgen per hour. Every pipe gets checked, every pump, every valve. Then chemical flushing begins. They run acid solutions through the primary loop piping. Sulfuric acid at 10% concentration. Temperature, 140 degrees Fahrenheit. Pressure, 115 psi. The acid dissolves the oxide film off pipe walls. Radioactive isotopes go with it. Solution gets collected in 13,000-gallon tanks, filtered through ion exchange resins. Radionuclides precipitate onto the resin. Resin gets incinerated at 2200 degrees Fahrenheit. You get ash. Mix the ash with cement and pour it into concrete containers. That's Class 2 radioactive waste. Chemistry doesn't work everywhere. Valves, gate valves, filters, they dismantle those by hand. Teams of 3. Shifts last 30 minutes. Can't go longer, the dose accumulates. Every part gets packed in a lead box. Box weighs 265 pounds. Walls, 4 inches of lead. If contamination levels run too high, they encase the part in concrete right inside the hull. Special attention goes to the reactor's biological shield. Massive plates of lead and polyethylene. Lead layer, 6 inches thick. Polyethylene, 12 inches. Lead stops gamma rays. Polyethylene slows neutrons. Weight per plate, 4 tons. 8 plates total. They pull each one with a crane. Decontaminate with ultrasound. Frequency, 40 kilohertz. Power, 3 kilowatts. Ultrasound breaks down the oxide film. Then they rinse the plate with alkaline solution and dry it with hot air at 250 degrees. Only after thousands of air samples and surface swabs, when everything reads 0, they open the dock to regular workers. Now it's not a nuclear facility, it's just a complex steel structure. Cutting the hull. After decontamination, the submarine is ready for final dismantling. The submarine's hull isn't ordinary metal, it's an alloy built for war. It withstands water pressure at depths of 1,000 to 1,300 feet. That's 30 to 40 atmospheres. Hull thickness, 3 to 4 inches. A K29 grade steel. Tensile strength, 100,000 pounds per square inch. Regular cutters won't touch it. They use plasma torches. Plasma is ionized gas. An electric arc creates the temperature. Voltage, 300 volts. Current, 400 amps. Power, 120 kilowatts. Argon gets blown through a nozzle 1/8 inch across. Pressure, 90 pounds per square inch. Flow rate, 1 cubic foot per minute. The arc heats the argon to 15,000 degrees Fahrenheit. That's 1.5 times hotter than the surface of the sun. The plasma jet shoots from the nozzle at 670 miles per hour. That's the speed of sound. Under that stream, 4-inch thick steel melts in 5 seconds. The torch follows the marked line. Cutting speed, 8 inches per minute. Sparks and smoke fly from the torch. Flame height, 10 feet. Spark temperature, 1,800 degrees. The second tool, oxygen lances, a 10-foot steel pipe, 1-inch diameter. Inside, a bundle of steel rods, each about 1/6 of an inch thick. Pure oxygen flows through the pipe at 150 psi. Flow rate, 50 cubic feet per minute. The rods are ignited with an acetylene torch. They start burning in the oxygen. Steel burns. Massive amounts of heat pour out. Temperature in the burn zone, 6,900 degrees Fahrenheit. The lance burns clean through the steel, leaves a molten seam 2 inches wide, burn through speed, 20 inches per minute, faster than plasma. But it takes serious skill. You guide the lance dead perpendicular, deviate more than 10 degrees and the burn's incomplete. Crews of 4. Protective suits made of Kevlar, masks with number 13 filters. They block infrared and ultraviolet radiation. Without the mask, your retina burns in 1 second. They cut from bow and stern, working gradually toward the center. The hull gets cut into cylindrical sections, each section 20 feet long, 30 feet in diameter. Weight, 400 tons. Cranes rated for 800 tons lift the sections and stack them in the sorting zone. Metal sorting. Every hull fragment gets checked again with dosimeters. They're hunting for isotope traces in microcracks and weld seams. If the device clicks, the fragment gets isolated, Sent for recleaning or special disposal. Only clean metal receives a safety certificate. It can leave the shipyard territory, then sorting by chemical composition. Steel grades HY80 and HY100. These are high-strength steels. Nickel content, 8%. Chromium, 2%. Molybdenum, 1%. These alloying elements are treasure for metallurgists. Nickel provides toughness. Chromium, corrosion resistance. Molybdenum, strength at high temperatures. Regular hull steel. AK-29 gets sent for remelting separately. Titanium parts, the sail, fairings, also separate. Titanium doesn't melt with steel. Different melting points. Titanium, 3,034 degrees Fahrenheit. Steel, 2,795. Copper alloys, wiring, heat exchangers, to non-ferrous metal. Aluminum alloys, bulkheads, ladders, to aluminum scrap. Reborn in fire. High-strength steel heads to the metallurgical plant. Loaded into an electric arc furnace. Capacity, 100 tons. 3 graphite electrodes, 24 inches in diameter. 600 volts, 60,000 amps. 36 megawatts of raw power. An arc ignites between the electrodes and metal. The arc zone hits 6,300 degrees Fahrenheit. Metal melts, becomes a liquid lake. The melt reaches 3,000 degrees. Melting time, 3 hours. Lab techs pull samples every 30 minutes. Analyze composition on a spectrometer. Adjust with ferroalloy additives. Precision matters. Carbon tolerance, plus or minus 0.05%. Nickel, plus or minus 0.1%. Finished melt pours into a ladle. The ladle weighs 200 tons. From the ladle, it flows into molds. Create slabs, steel plates. 6.5 feet by 20 feet. 10 inches thick. 23 tons each. Slabs get rolled into sheets or cut into rebar stock. Yesterday's warship armor plating becomes a river bridge support or a skyscraper skeleton. Steel that once withstood depth charges now holds up bridges. Metal doesn't die. It lives again. If you found this fascinating, hit that like button. Drop a comment. Did you know submarines get recycled for 300 years? Subscribe. We show you how the old dies and the new is born. There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to become a cylinder with a 55-inch diameter. For those of us who remember when heavy industry was the backbone of manufacturing, this is the kind of craftsmanship that built the world we know. The star of this operation? The plate rolling machine. And let me tell you, this Italian marvel is about as perfect as metalworking equipment gets. The company's been perfecting this craft since 1946, right after World War II, when Europe needed reliable machinery to shape the infrastructure of the modern age. The machine operates on a 3-roller pyramid principle, which has been the gold standard for rolling heavy plates since the Industrial Revolution, though the precision we're seeing here would have blown the minds of craftsmen from that era. Here's how this beautiful process unfolds. A steel plate, which has been preheated to reduce brittleness, gets positioned between 3 massive cylindrical rollers arranged in a triangular configuration. The 2 bottom rollers are the driving force, rotating in synchronized harmony to pull the plate through, while the top roller, which can be hydraulically adjusted to within fractions of a millimeter, applies downward pressure, creating the curvature. Think of it like rolling out dough, except this dough weighs several tons and could support a building. The operator, working from a computerized control panel, inputs the desired diameter and thickness parameters. The machine's sophisticated sensors continuously monitor the bend radius, making real-time adjustments through hundreds of hydraulic cylinders. Remarkably, despite working with such massive forces, the machine achieves tolerances that would make a Swiss watchmaker proud. The plate makes multiple passes through the rollers, bending a little more each time, gradually approaching that perfect cylindrical form. This incremental approach prevents stress fractures and ensures uniform curvature along the entire length. As the plate begins its transformation, you can actually see physics at work. The outer surface of the bend stretches while the inner surface compresses, and the metal flows like frozen honey, maintaining its structural integrity while taking on this new shape. Now, let's step into the world of heavy forging, where tradition stretches back to the blacksmiths of ancient Rome. Except now we're working with hammers that make Thor's hammer look like a toy. What's especially mesmerizing is the combination of raw power and surgical precision. We're watching parts being forged that can weigh up to 250 tons. The process begins long before the hammer ever strikes. Steel ingots, fresh from the mill, are slowly heated in gas furnaces to temperatures around 2,200 degrees Fahrenheit. This isn't a rushed process. Depending on size, heating can take anywhere from 8 to 24 hours. Once the steel reaches that perfect forging temperature, glowing that unmistakable orange-yellow color that means it's ready to flow, the real dance begins. Massive manipulators, essentially industrial robotic arms that can rotate and position these multi-ton pieces with remarkable delicacy, move the workpiece under the forging press. Both hydraulic presses and mechanical hammers are used, depending on what the job demands. A hydraulic press applies slow, steady pressure, ideal for ensuring the force penetrates deep into the heart of the piece, eliminating any internal voids or inconsistencies. The mechanical hammer, on the other hand, delivers rapid blows that shape the surface and create specific forms. The forge master, a craftsman whose skills require decades to develop, orchestrates this symphony of heat and pressure. Between each strike or pressing, the piece rotates, gets repositioned, and sometimes reheated. This is called open die forging, because unlike closed die forging, where metal is compressed into a specific shape, here the masters are literally sculpting the metal through repeated strikes and pressure applications, gradually drawing it into the desired form. Each strike refines the grain structure, making the steel stronger and more reliable than anything achievable through casting or machining alone. Now let's move on to modern precision forging, which has adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small batch artisan forging. The process starts with steel bars, often supplied in coils, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion, but within seconds a steel billet placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. The secret lies in electromagnetic induction, discovered by Michael Faraday way back in 1831, but only practically applied to industrial heating in the early 20th century. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2,000 and 2,300 degrees Fahrenheit. Depending on the steel grade, the billet moves to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. What's remarkable is the speed and precision of modern forging presses. We're talking about machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. There's something deeply satisfying about watching skilled craftsmen build storage tanks. The process begins with selecting and cutting steel plates. Modern fabrication shops use CNC cutting tables, plasma or laser, that can slice through thick steel plate with remarkable precision, following computerized patterns that ensure minimal waste. But before any cutting happens, there's meticulous layout work, figuring out how to arrange different components to get the most from each plate. It's a puzzle that combines geometry, efficiency, and material science. After cutting, the components move to rolling and forming operations. Tank shells typically need to be cylindrical, which means flat plates must be rolled into curves using 3-roll bending machines like the ones we saw earlier. The edges of these rolled sections are then prepped for welding, usually with beveled cuts that let the weld penetrate completely through the material's thickness. The welding process, that's where the craftsmanship really shines. Tank fabrication typically uses submerged arc welding for the main seams, a process where the arc works under a blanket of granular flux, protecting the weld from atmospheric contamination while allowing deep penetration and high deposition rates. End caps, whether they're flat, dished, or hemispherical, get fitted and welded on, and then comes the real test, hydrostatic testing. The completed tank gets filled with water and pressurized above its operating pressure to verify integrity. Any leaks or weaknesses show up here, not during service, which could be catastrophic. Let's wrap up with the 3-roll plate bending operation, because there's something fundamentally impressive about watching these machines transform flat steel into curves with such apparent ease. The 3-roll bending machine is one of those elegant engineering solutions that's remained fundamentally unchanged for over a century because, simply put, it works beautifully. The machine consists of 3 essential rollers arranged in a pyramidal or triangular configuration. The 2 bottom rollers are drive rollers that grip and feed the plate through the machine, while the top roller, which can be adjusted up or down hydraulically, provides the bending force. The beauty of this setup is in its simplicity and efficiency. By varying the top roller pressure and making multiple passes, you can achieve a wide range of diameters and even create nearly perfect circles. The process itself is mesmerizing to watch. The plate enters between the rollers, and as they rotate, you can literally see the flat material take on curvature. For thicker plates or tighter radii, multiple passes are necessary, with each pass increasing the curvature incrementally. Modern machines can handle impressive specs. Plates several inches thick and many feet wide, bending them into cylinders or cones with remarkable precision. The rollers themselves are precision-ground, hardened steel, designed to maintain their shape under enormous loads. This technology represents a perfect marriage of time-tested mechanical principles with modern control systems, creating tools that are simultaneously powerful and precise, capable of forming the steel that builds our world. Deep beneath southwestern Poland, in the Lower Silesia region, lies one of the planet's largest copper deposits. 1.5 billion tons of ore, 21 million tons of pure copper, enough reserves to last several more decades. Here, at depths reaching 4,600 feet, that's 140 stories down, operates the company KGHM Polska Miedź. Every year, it brings to the surface nearly 400,000 tons of copper, the only European mine in the global top 10 of largest copper producers. But that's not all. Along the way, they extract silver in such volumes that KGHM is the world's #1 producer of this metal. Gold, nickel, lead, rhenium, selenium, platinum, from a single ore. Today, we're descending into this underground world, following copper's entire journey, from black rock nearly a mile down to shining wire, without which every factory, every phone, and every electric vehicle on the planet would grind to a halt. Poland's copper story begins in 1957. Geologist Jan Wijekowski was drilling a borehole near the town of Złotorysia when he hit an ore body so massive he didn't trust his own instruments at first. 43 miles long, 12 miles wide, The Legnica-Głogów copper belt turned out to be one of the largest deposits on Earth. By 1961, they'd sunk the first shaft. Today there are three: Rudna, Lubin, and Polkowice-Sieroszowice. Rudna is the biggest. Its levels stretch underground across 36 square miles. That's roughly the entire center of Warsaw. The ore sits in three types of rock: sandstone, shale, and dolomite. Layers of copper mineralization, chalcocite, bornite, chalcopyrite, plunge downward like pages of a giant book, tilted at an angle to the horizon. Average ore body thickness, 3 to 10 feet. Copper content, 1.5%. Which means, to get 1 ton of metal, you need to haul up and process 67 tons of rock. Before mining can start on a new level, you need to sink shafts. Vertical tunnels about 26 feet across. Here's where things get tricky. Aquifers. When they drilled the first shafts back in the 60s, the rock was saturated with water under massive pressure. Standard drilling? Instant flooding. KGHM engineers developed a unique solution: freeze the rock solid. Around the future shaft, they drilled 8-inch boreholes in a circle, pumped in calcium chloride chilled to -22 Fahrenheit. 3 to 6 months later, the water in the rock around the shaft turned to ice, creating an ice wall several yards thick. Only then could they start drilling the shaft. Today, the new GG1 shaft in Polkowice, commissioned in 2024. Depth, 4,416 feet. That's the deepest mining structure in Poland and the largest underground project in European non-ferrous metallurgy. At 4,400 feet down, the rock temperature hits 104 degrees Fahrenheit. Without air conditioning, people wouldn't survive. KGHM built a massive underground cooling system. Refrigeration units pumping over 50 megawatts chill air down through ventilation shafts. Miners work at the face in temperatures around 82 to 86 degrees. The mining method? Room and pillar. Miners use specialized low-profile drill rigs, just 5 feet tall because the ore seam is the same thickness, to drill holes into the roof and walls of the working face. These holes, up to 13 feet deep, get packed with explosives. After the blast, rock collapses into the chamber. But it's not that simple. Rock pressure at 4,400 feet? That's 8,000 tons per square meter. Rock under that kind of pressure behaves unpredictably. KGHM created a unique seismic monitoring system. Hundreds of sensors throughout the mine detect the slightest tremors. A computer analyzes data in real time and warns of rock burst risk minutes before it happens. Over 60 years, this system has saved thousands of lives. The blasted ore is loaded by load haul dump machines, massive diesel-powered scoops with remote control. The bucket capacity is 10 cubic meters, about 25 tons of ore in a single scoop. The machine hauls the ore to a transfer point, where it's dumped into an ore pass, a vertical shaft 5 feet in diameter, through which the ore falls downward by gravity to a level with conveyors. The conveyor system in the Rudna mine spans over 300 miles of belts. The ore moves toward the shafts at 13 feet per second. At the base of the hoist shaft, it accumulates in a bin with a capacity of 1,000 tons, from which it's loaded in batches into the hoisting vessel, the skip. The skip, with a 30-ton capacity, rockets upward at 52 feet per second. That's almost 40 miles an hour. The climb from a depth of 3,300 feet takes 70 seconds. Each hoist shaft delivers between 25 and 30,000 tons of ore to the surface every day. On the surface, the ore is hauled to the processing plant. Here's where the first bit of magic happens. Copper content in the ore? 1.5%. That's way too low for smelting. We need to bump it up to 23%. The ore gets crushed in cone crushers down to half-inch chunks. Then it heads into ball mills, horizontal drums about 16 feet across packed with steel balls. The drum spins, the balls tumble, and they grind the ore into powder, particles smaller than 0.04 inches. This finely ground slurry gets pumped into flotation machines, rectangular tanks holding up to 26,000 gallons each. Special reagents get added, xanthates and frothing agents. Compressed air bubbles up through the slurry from below, creating millions of tiny bubbles. The reagents make the surface of copper minerals hydrophobic. They repel water. Air bubbles stick to the copper particles and drag them to the surface as foam. The waste rock sinks to the bottom. Scrapers skim off the foam. That's copper concentrate with 23% copper content. One flotation cycle pulls out 88 to 90% of the copper from the ore. The concentrate ships to the copper smelter in Głogów, one of KGHM's 2 plants. They use a single-stage flash smelting technology. The concentrate gets dried to 0.3% moisture and fed through a burner into the smelting furnace shaft. At the same time, they blast oxygen in. Not air, but pure industrial oxygen at 95% purity. Suspended concentrate particles ignite in the oxygen stream instantly, in fractions of a second. Temperature in the reaction shaft hits 2,550 degrees Fahrenheit. Copper sulfides oxidize, releasing massive amounts of heat. The reaction's nearly self-sustaining, requiring very little additional fuel. At the bottom of the settling chamber, 2 melts separate. Matte, a molten copper sulfide at 65% copper content, and slag, a silicate melt with waste rock. The slag gets drained and processed separately. They still extract copper from it using additional flotation. The matte goes to the converter. Oxygen gets blown into the converter with the molten matte. A second oxidation happens. Sulfur burns off. Iron oxidizes and shifts into slag. What's left is blister copper, 98.5% pure. But we're not done yet. The blister copper gets cast into anodes, plates 3 feet wide, 3 feet tall, 2 inches thick, weighing 660 pounds each. They're hauled to the electrolytic refining shop. Here, tanks 20 feet long, filled with a solution of copper sulfate and sulfuric acid. Into each tank they hang alternating anodes and thin stainless steel starter sheets. A direct current runs through the solution, about 60 amps per square foot. Copper dissolves from the anode, travels through the electrolyte, and deposits onto the starter sheet. After 12 to 14 days, a cathode builds up on the sheet, a plate of pure copper weighing 130 pounds at 99.99% metal content. That's grade A, the highest category of exchange copper on the London Metal Exchange. Everything else, gold, silver, platinum, palladium, selenium, settles to the bottom of the tank as anode slime. It gets collected and sent to the precious metal shop. From this slime, KGHM pulls 1,200 tons of silver every year, more than any other producer in the world. Some of the cathodes get remelted and rolled at the Sardinia plant into copper wire rod, wire about 1/3 of an inch in diameter. This is the key intermediate product for the cable industry. The wire rod gets wound into coils weighing 5 tons and ships out to cable factories across Europe. All told, nearly 400,000 tons of copper flow from Polish mines through all these stages every year. 24 million tons of ore hauled up from below. 34,000 workers. All of it, for a metal without which modern civilization simply couldn't exist. Where does all this copper go? First, power. Every cable, every wire, every transformer winding, copper. The entire electrical infrastructure of the planet runs on this metal. Without it, you can't transmit a single watt of energy from the power plant to your outlet. Second, construction. Every modern home hides between 220 and 440 pounds of copper pipes and wiring. Water supply systems, heating, air conditioning, copper everywhere. Third, electronics. Your smartphone contains about half an ounce of copper. Not much, except the world sells 1.5 billion phones a year. Computers, servers, circuit boards, the copper traces are visible to the naked eye. Fourth, transportation. A typical gas-powered car contains 51 pounds of copper. An electric vehicle? 132 to 183 pounds. Power cables, motor windings, battery bus bars. Fifth, renewable energy. One 3-megawatt wind turbine uses about 4 tons of copper. Solar panels, copper bus bars collecting current. The world is shifting to green energy, and every step of that transition increases copper demand. Forecasts predict demand will grow 70% by 2050, which means those KGHM mines beneath Polish soil will keep running non-stop for decades to come. I'm standing at the shaft of the Rudna mine. The hoist roars as it delivers another skip full of ore. 30 tons of black rock that'll become wires inside Danish wind turbines in a few weeks. Cables under the English Channel. Windings in Berlin subway motors. Connectors and servers storing your cloud photos. Copper is the blood of technological civilization. It flows invisibly through everything that runs on electricity. And every single gram of this blood begins its journey right here, in the darkness beneath Polish soil, where people in hard hats work a mile underground to make our lives possible. If you found this interesting, hit that like button. Drop a comment and let me know. Did you know Poland is the world leader in silver production? And subscribe. This is where we open up the industries behind every object in your life.